Okay, let me just. Hi everyone, happy to have you join us. Hi. I know it's quite late for some people. It could be very early for some of you. If you are from the Mexico, like America side, I know it's quite early for you guys. But we're happy to have all of you join us today. For you, it's perfect. 6 p.m. It's a little late for us here. It's 8:30 p.m. for us. So we're having a a bit of a cozy evening webinar. But yeah, thank you all for joining us for our first kind of knowledge sharing webinar as part of the whole International Space Challenge series of webinars. We have quite an exciting webinar planned for today by Gang Kai, or Dr. Gang Kai, who is a research associate at the NASA Goddard Space Flight Center. So he's tuning in from the US, from the east side of the US. So he's right there with you guys on the early time zone. It's 8:30 a.m. for him. But yeah, if you're not already familiar with how we do things around here, the chat is always open for you guys to share your thoughts, share your opinions. But if you have any questions specific to the webinar for Gang Kai, please post it in the Q&A chat, in the Q&A box, which you can find at the bottom of your Zoom screen, because then it's easier for us to track and we won't lose track, we won't lose any of your questions, and we can try to address all of them at any point. You're free to post questions as and when the webinar is happening, but we will address them whenever we come out at an appropriate point of time, right? Okay, so with that said, Gang Kai, are you there? Oh, you're still muted, Gang Kai.
Hi everyone.
Yeah, so I'll hand it over to you. You can feel free to take over and yeah.
Okay, sounds good. Let me try to share my screen. All right. Can you guys see my screen right now?
Yep, we can see it. You might want to put on full screen.
Okay.
Yeah. Okay, that's great.
All right. Okay, perfect. So I'll just go ahead and start then. Yeah. Okay. Hi everyone. Thank you so much, Jillian. Thank you so much, SSTL, for inviting me to give this presentation. And thank you so much for you guys to come for those early in the morning or even late on the Friday night to join me. So my name is Gang Kai, and I'm a research scientist at the NASA Goddard Space Flight Center. And I'm also a lecturer at the Catholic University of America. So I'm just going to give an introduction on space weather today. Okay. So so a little bit about myself. Sorry, let me. Okay, so a little bit about myself. So I graduated from Colorado in physics and astronomy about a decade ago, and then after I did my undergraduate in Colorado, I went on to Michigan to study space science and plasma physics for my PhD, and that's where I got my doctorate. And then after a year later, I got my position as a research associate at the Planetary Magnetosphere Lab at Goddard Space Flight Center. And it's just recently that I actually I started teaching a course at Catholic University of America on space weather systems. Okay, and so my research topic is really a little bit wide. So I usually do data analysis, comparison with numerical models. I'm also trained in space plasma physics, planetary science, space weather, and the Earth's and planetary magnetosphere, which is all encompassed under this large umbrella of heliophysics. I was also involved in the MESSENGER mission, which is NASA's mission to Mercury, the MMS mission, which is a Earth mission, and also MAVEN, which is the NASA's mission to Mars. Okay, so So let's go into the definition of space weather. So what is space weather, right? I mean, that's the large title for this. That's the overarching theme for this challenge. So space weather is pretty much as defined by the the Space Weather Prediction Center at NOAA. Is the study of the variations in the space environment between the Earth and the Sun. So there's really a Earth-Sun connection right there. And it describes the phenomenon that impacts systems and technologies in orbit and on Earth. So really, we are also studying how does this Sun-Earth connection, Sun-Earth interaction impacts Earth, impacts the human society and our reliance on technology, on satellites, everything in the space, or even on Earth itself. Okay, anything that runs on electricity, how does it impact us? All right. So with that definition, space weather really covers everything. Okay, because it's the sun to the Earth, it covers everything from the surface of the sun all the way through the entire interplanetary medium. Okay, the interplanetary space between Sun and Earth, and also the Earth systems itself, the Earth plasma environment, and also even all the way to the edge of our solar system. Okay, and now this is where we are going into the planetary science, because as humans, we are actually always looking further out into the stars, right? And we want to explore more of the solar system, not just being on Earth or within Earth's system. So we are looking to go to the moon, to the Mars, and all this. This is where space weather comes in. Okay, so really, as I always tell my students, space weather is a multidisciplinary applied science because it spans across a lot of field of study. You can be a solar physicist, you can be heliophysics, you can be a planetary scientist, you can be astrophysicist, you know, or even engineering. You know, I have met a lot of engineers during my career, and we have electrical engineers and all sorts of engineers, you know, mechanical engineers also. So we all come together, think of the problems, the solutions, and how do we send flight missions to answer the questions that we have. Okay. So first, of course, we have to talk about the sun, right? It's the giver of life, right? And sorry, 1 second. Okay, so yeah, so we have to talk about the sun, and so this is I will call it a skeleton anatomy of the sun. Okay, so of course we have the sun interior, which makes up of the core, the radiative zone, the convection zone. Now these are the things, these are the parts of the sun that we can't really see because they are inside of it, they are within the sun, and a lot of these are pretty much theory and numerical modeling of what we think is happening within the sun. Okay, so we're not going to touch a lot on that, but we are going to touch a little bit on the first layer that we can see, which is the photosphere. The photosphere is the surface of the sun, and anything below this layer is opaque because the photosphere is where the lights are emitted, and that's where we can see them. Okay. And so on the photosphere, there is a phenomenon that is very interesting, and it's quite literally the start of any space weather. Okay, so and these are called the sunspots. Now, sunspots, as you can see labeled there, sunspots are kind of like blemishes on the surface of the sun. Okay, so they appear as dark spots on the photosphere, and they are regions of intense magnetic field. Now, do know that the sun, just like any other celestial body in the solar system or in the universe itself, it generates its own magnetic field. Okay, and so these sunspots are region where it is of intense magnetic field, and it usually occurs in pairs. Okay, and it has an opposite polarity, a positive and a negative polarity to it. And the reason why they occur darker is because the strong magnetic field suppresses the heat transfer, and hence this because it suppresses heat transfer, so these sunspots are actually cooler, and so that's why, because they are cooler, they appear darker as compared to the rest of the photosphere. Okay, and sunspots are very important because they are often used as a proxy for solar activity. So which means that when solar physicists look at the sun, right, the more sunspots they see, that's where they start to sweat, because when you have more sunspot, that is the source of solar activity, and this also means that we might be seeing a lot of space weather activity at Earth. Okay. So usually, in the past, I mean, even now they are counting sunspots, and they are labeling it, giving it some sort of like a number to it, so that they can keep track of every sunspot as the sun rotates around. Okay. So the next layer is the solar corona, which is the a hot outer envelope or atmosphere, okay, of the sun. And anything beyond this solar corona is what we call by the solar wind, which is pretty much an outflow of plasma, which is a mixture of ions, electrons, and protons. Okay, and it's an outflow of this coronal gas from the solar wind. So that's what the solar wind is. Sorry, it's an outflow of a coronal gas, and that's what the solar wind is. That's the solar wind. Okay, and from the solar wind, it goes all the way out to the edges of the solar system. Okay, and it actually reaches the what we call by the heliosphere, in which actually that forms the boundary between the sun's magnetic field influence and also the intergalactic medium. Okay, now the intergalactic medium also has its own so-called plasma, and that interacts with the solar wind. So in a way, the solar wind kind of protects us against whatever that is outside of our solar system also. Okay. Now the solar wind also carries the sun's magnetic field, and it contains mainly of protons and electrons, some traces of alpha particles, and heavier particles, heavier ions, and it's the interaction between these particles and the sun's magnetic field that actually can cause is the interaction between all the solar wind magnetic field and also the particles with the Earth's magnetic field that actually creates space weather here that we observe, okay, at Earth. So we're going to talk a little bit more about sunspot here. So sunspot is, like I said, is the dark spots on the sun, and they're quite big, right? I mean, here is a figure of a sunspot, and when we enlarge it and we scale it, we kind of show like a size of Earth. It's actually almost as big or bigger than Earth, and these are some of the smaller sunspots that we usually see. Okay, so sunspots occurs in a cycle of 11 years, and at each cycle, the sunspots will appear preferentially appear at the mid-latitude and slowly progress. So mid-latitude means that they are at higher latitudes. I don't know whether you can see my cursor. They occur at higher latitude, and they will gradually progress into the solar equator right here. Okay, so here I have a diagram that shows that. Right, so these are the this entire figure spans across almost more than 100 years, and you can see that for each cycle, right, the number of sunspots starts at around 13 degrees north and south of the sun, and then as each cycle progress, they actually move slowly towards the equator, which is denoted here by the EQ. All right. And then the cycle repeats itself. And so this is what we call by a butterfly diagram. Okay, now there are some times where there is little or no sunspot observed, and this is what we call by the solar minimum. And there are times where the sunspot numbers peak, and this is what we call by the solar maximum. And so you can see here, it's the same time period from 1870s to 2020. All right, and you can see that the figure on the bottom panel shows the number of sunspots. So they are counting sunspots. People are counting a lot of sunspots. And before, you can see that between 1870s and 1910, there's not that much of a sunspot even during the solar maximum. Okay, and you can see this cycle, right? So at each peak, there's the solar maximum, and at each the minimum number of sunspot observed, that's the solar minimum. All right, and the highest number of sunspots during the solar maximum was at 1960s, and then it has been a decreasing downward trend since then. Okay, and even right now we are at our lowest solar maximum. Okay, and so this is the prediction for the sunspots number. Okay, our current solar cycle has one of the lowest. It's one of the lowest solar maximum that we have ever recorded, and we aren't sure why, because there's so much things that we do not understand about the sun, right? And because the thing is that we can't really send spacecraft too close to the sun because of issues of like having the heat and things like that. So and the radiation. So we can't really do that. So we can't really probe deeper into the solar atmosphere. So all we can do is really predicting, and sometimes the prediction may not even be accurate, and we will only know as we go further into the particular solar cycle. Then we kind of know that whether this will be a weak solar maximum or a strong solar maximum. Okay. So the next thing that we want to talk about is prominence and also flares. And so these are the two things that actually will eject materials, so plasma materials from the sun, okay, outwards into the solar system, okay, into the interplanetary medium, and they do so in a very violent and abrupt way. Okay, these are the ones that are sending like particles that are really energetic, really radiations out into the solar systems and the solar system, and that's when it will reach Earth, and that's how geomagnetic storms and all the space weather activities start to occur. Okay, so I'm going to play a video to kind of explain it, and it does a very good. It's a video on the NASA website, and it does actually a very good job at explaining what is a coronal mass ejections and solar flare. It does come with very cool music, so enjoy it. Oops, sorry. Okay. Okay. So, all right. So from the video, you can pretty much so the video explains a little bit on what we mean by so what's the difference between when we talk about coronal mass ejections and solar flares. So what happened is that because the sun has its own magnetic field, and the sun is like a block of plasma. Okay, and as it rotates, it twists the magnetic field so much that that the magnetic field become very complex and twisted, and it will start to emerge from the interior of the sun, and it forms the prominence that we see. Okay, which are like if you can see that it forms like a tube coming out from the sun, And through some process, which I will not go into, and it's kind of like an advanced space plasma physics type of concept, but it's a process that we call magnetic reconnection that actually can violently release all these hot plasma trapped within these prominences, and they will be ejected away from the sun into the through the solar wind and into the rest of the solar system as coronal mass ejections. Okay, and sometimes coronal mass ejections occurs with what we call by a solar flare, which is like as you can see from the video, it's like a bright flash of light, and those are the ones that actually come as a form of X-rays. So they are kind of coming as a light radiation, and they could reach. These are the ones that reach Earth the fastest, because a coronal mass ejection is ejected away from the sun, right, at a certain velocity, and it will take like hours or days before we can actually encounter it, before we can actually feel its effect. But the X-ray, the X-rays, the radiation from the solar flare is the one that will reach us first. And as the video has shown, it will reach us in only 8 minutes. Okay, so there's really not a lot of time there's not a lot of time in between from the time that we see it, right, and we actually observe the effects on it. And X-rays are very dangerous because they're the ones that actually can affect radio blackout in our atmosphere and things like that. Okay. So so now what happened? What happened when this coronal mass ejection, as we call it, right, CMEs in short, reaches Earth? So quite frankly speaking, this is what space physicists always say, is that life as we know wouldn't have existed if our Earth doesn't have a magnetic field to protect ourselves against this coronal mass ejection. Okay, there are a couple of planets in the solar system that does not have a magnetic field to do so, and two of them being Venus and Mars. And so that's the reason why we believe that Mars' atmosphere is so thin and that it has always been stripped away by all this coronal mass ejection by the solar wind itself. Okay, but I will not go into that. So I'll actually go deeper into the interaction between the CMEs and Earth. Okay, so we know that Earth has a magnetic field, right? And in the simplest sense, it's like a bar magnet. Okay, so you have the North and the South Pole, right? And ancient people has already known that Earth has a magnetic field, because we have compasses, we have like rudimentary compasses that actually helps in sea navigation and things like that. They have made use of that, right? And so, of course, we know that the Earth magnetic field is far from being a dipole, but it's a good approximation, but it's highly complex, okay? And it's likely to be generated through a dynamo process within the Earth's core. Okay, so the Earth magnetic field serves as a protective shield, a magnetic shield, okay, against the solar wind and the CMEs. Right, and it's it is actually the interaction between the sun's solar wind, CME, and the Earth's magnetic field that actually forms what we know as a magnetosphere. Okay, so just like the atmosphere, right? Earth has an atmosphere around, and that's what we feel, we see. The magnetosphere cover a larger volume in space, in outer space. And we can't see it, but we can observe it through our instruments, but we can't really see it. Okay. And so under the right conditions, however, these particles can enter the Earth space environment, or it can enter so-called leak into the Earth's magnetic shield and create what we know as a geomagnetic storm. Okay, so this is actually a very nice video. Unfortunately, there's no sound to this, but this is a nice video to show what we mean. How does the CME interact with the Earth's magnetosphere and create what we know as a geomagnetic storm? Okay. So you can see that the CME is being ejected out from the sun as like a block of plasma, and that's you can see that it goes around the magnetosphere. So that's where the magnetosphere actually protects against it. But through some certain processes and under certain conditions, it can actually go into the inner magnetosphere, right, and interacts within the magnetosphere itself and creates, auroras. But it also means that all these particles can actually interact with other things within the magnetosphere itself. Okay, so what is a geomagnetic storm, right? We have been talking about it, and so what exactly it is? What exactly is it? So it is defined as a major disturbance of the Earth's magnetosphere, okay, that occurs when there's a very efficient exchange of energy from the solar wind into the space environment surrounding Earth. Okay, so so I have highlighted some of the important keywords here, which is major disturbances. All right, and it's a very efficient exchange of energy between the CME and Earth, and this is when the energy actually enters into the Earth systems and create geomagnetic storms as we know it, right? And also it has to be intense, long lasting, and energization and intensification of the ring current, which in other words is also the radiation belt, which is part of the theme for the open category. Okay, so so as physicists, we always like to quantify things, right? Because some of these explanations are qualitative at best, and so we need something to quantify. How do we define a quantity to define geomagnetic storm, right? And so we usually use something called the DST index. Okay. So what is the DST index? So the DST index is actually a measure of intensity, okay, of the geomagnetic storm using 4 ground-based magnetometer measurements at low latitude, and we average it over 1 hour. Okay, so these are the 4 stations, and I have shared with you the geographic and geomagnetic positions of these 4 stations. So the Earth's magnetosphere is actually surrounded by many different current systems, okay? And any of these perturbations, any perturbation from the geomagnetic storm can cause changes in the magnetic field, okay? And these changes in the magnetic field, okay, can be detected and measured by instruments called on the ground called the magnetometer. Now, for any one of you who might be wondering, or any electrical enthusiast or something, you're wondering what is a magnetometer, right? So as the name suggests, right, a magnetometer is a device that measures magnetic field. Okay, we already know we have already deal with a magnetometer on a daily basis. Actually, a compass is a magnetometer, for example, because it does measures the magnetic field. Okay, so so often or not, it is considered the most reliable and most important instruments for any space exploration mission. To be honest, and given its long heritage in various missions. And so usually for any space missions to study any plasma phenomenon in space, there has to be a magnetometer, because magnetic field just is everywhere. Okay, and particles are usually affected by changes in the magnetic field. All right. So this is an example of a 30-day DST plot for the 2003 Halloween superstorm, which I will talk about later. Now, usually a change in so you can see that this spans over 30 days, and usually when there's quiet times, there's no storm. The DST, the change in the magnetic field of Earth magnetic field, usually hovers around 0. But when it starts to get a little bit intense during the storm time, it will start to decrease at -50 to -100. Now, anything more than a change in a decrease in the magnetic field of more than 250 nanotesla is considered a superstorm. And thankfully, there is not a lot of them, that we have encountered so far. So in a sense, it will be equivalent for people in the US. It will be equivalent of like a Category 5 hurricane. Okay, that happens once in a few decades, and this is an example of the 2003 Halloween storm, where you can see that the DST actually decreases up to between 350 nanotesla to 400 nanotesla, and that's what we consider a superstorm. Okay, and of course the DST index is not the only measure of a geomagnetic storm used by scientists, although it is the commonly used. So there are a lot of other indices out there that we usually use. Okay, so there are different classification of storms and solar flares. Now, as you probably now have realized that space weather has a lot of similarity with how we define and how we talk about climate weather, right? On Earth weather at Earth. So we, for example, at Earth we have hurricanes, we have earthquakes, right? Some of these major natural disasters right out there. Right, and we have categories for them, right? So for example, hurricane. Right now, I mean, just a couple of days ago, the U.S. Eastern side has been hit by a Cat 4 Hurricane Ida, for example, and so we have a category for them based on, for example, a hurricane based on their speed, right? So we also do have categories for storms and solar flares, all right, geomagnetic storms and solar flares, and these are the categories out there. So for radio blackout caused by solar flares, right, you have the when we talk about M1 flare, what does it mean? So you can see that so they shows this. So this is a chart by the NOAA Space Weather Prediction Center. They have R1 to R5 being extreme, and they have all the effects of it. And this is what we mean by M1, X20, solar flare, or M1 flare. X20 being the largest, M1 being the weakest flare. All right, and they also gave you the frequency of it. Okay, and then And then we also have a similar table for the geomagnetic storm. All right, and so if you ever heard someone talking about the KP, right? So KP5 to KP9. KP9 being like extreme geomagnetic storm, and that's the one that we just discussed a little bit about before about the 2003 Halloween storm. Okay, so now the thing is that so just by categorizing these storms, we can kind of like get a good sense of how what is the intensity and magnitude of each storm. Now, however, just like for example, any scale that we have for earthquakes or hurricanes, these are exponential scales, and they actually saturate really quickly at Category 5. For example, here R5 or G5, and anything above that, there is no category for that. So so we pretty much do not know anything about any storms that are more extremes, and we know that those storms exist. And so this categorization was created a very long time ago, and is really due for a revision as our scientific understanding of space weather improves. Okay. And so just like any major natural disasters, and only those most destructive ones make the headlines, right? We won't be having having headlines of a small rainstorm, occurring in a specific location. So now then the question is, have we ever encountered a superstorm, and what impact does such a superstorm has on our technologically reliant society? And the answer is yes, of course, and we have met quite a number of them throughout the decades that we have actually known about geomagnetic storms. Okay, so of course, the first thing that we talk about the effects of storm is the aurora borealis, which is the northern lights. So the first thing that these storms can create is these northern lights. Okay, and during storm time, these northern lights will be intensified. Okay, and they can be seen at lower latitudes. Now you don't need. Now you do have to. I do have to note that you do not need a geomagnetic storm to observe the northern lights. Merely the interaction between the solar wind and the Earth's magnetic field can create beautiful auroras in the northern and southern hemisphere. Okay. Now we usually only talk about the northern hemisphere because in the northern hemisphere there is more land mass to observe this phenomenon, and they usually occur at higher latitude. So we are talking about, during normal quiet times, we are usually talking about northern Canada, Scandinavia, and things like that. Okay. So if you really want to observe northern lights, you have to go very far up north. Okay. Now during a geomagnetic storm, this is a little bit different. Okay. So during storms, this aurora can intensify, become more intense or brighter in that sense, and it can actually be observed at lower latitude. Okay, very low latitude. For example, there are some storms where we can even see until Texas, for example, which is like one of the southern states in the US, or even Florida. Okay, so for example, the largest storm, the most popular story that we always like to talk about, right, is the largest storm ever recorded, and that is known as the Carrington event in 1859. We're going to talk about it in the next slide a little bit more. But the people has recorded observation that the lights are so intense that people can even read a newspaper under the aurora, and it got so bright that people even start preparing breakfast, thinking that it's already morning time. Okay, so this is how a superstorm can create really bright auroras. All right, and so this is just a quick summary of like how aurora is formed, and during interaction between the solar wind and the Earth's magnetic field. Okay, so this is a very cute cartoon diagram. So at high latitude, we talk about is being normal. As you move further down, it's cool and exciting. As you get really further down, someone should really go check on our satellites. And if we reaches the equator, so I'm from Singapore, right? And Singapore, Singapore is near the equator. And if we ever see something like that in my country, then it will be bad for whoever that is operating the satellites up there. But for space physicists, that is going to answer a lot of questions that we have right now. Okay. So this is the 1859 Carrington event that I talked about earlier on, and this is D. Note that I highlighted D because this is the event that everyone in studying space plasma physics or space weather, right? This is the first thing that they study. Okay, this event here. So this is known as the Carrington superstorm of 1859. It is the most powerful storm ever recorded, and it remains a textbook example of what a superstorm will look like. Okay, and it occurs in 1859, right at the point where scientists are beginning to observe and track all the sunspots on the sun, and it was named after Richard Carrington, an astronomer, who is actually at that point in time observing and making sketches of the sunspot, as you can see from this illustration here. And so this superstorm occurs during a time where electricity-based technology is still at its infancy. Okay, we are just barely using electricity to power up lights and for telegrams, for example, which is like the first generation landline phone for those of you old enough to know what a landline is. And at that point in time, when they saw this, they saw the flash, they saw like all these auroras being formed, all these effects of the space weather, right? Effects of the storm that it caused. They did not understand the physics behind it. They can only see the flash, by the way. They can't see the coronal mass ejection that is being that is coming towards Earth, right? So they don't understand the physical phenomenon caused by the superstorm. But we do actually have a good account and records of the effects of this storm. So that's the reason why we are able to study this event in as much detail as we can. Okay. So these are some of the auroras, reports of the aurora caused by this 1859 superstorm. And one of the most interesting account is actually right. I don't know where you can see it right here at the bottom, where you can see that Sabine is a merchant ship. Okay, it's located at the lower latitude, at latitude of 11 degrees. So it's actually kind of like as close to the equator as you can. As you can, and that's why they see the deep rosy red aurora as shown by the figure here, the diagram here. Okay, and so this is the effects on the telegram itself, and you can see that even with the batteries being disconnected from the telegram, the between Boston and Portland operator, they can still communicate because of the induced electricity that is caused by the storm itself within these lines. Okay, and it's a very interesting read, and you can go read on it at your own time. So this is the other storm that is more recent. Is the 2003 Halloween storm that we talked about, and you can see now we have observations of this, and you can see how like the sun is giving out all the releasing the CMEs out into space, and you can see right here, right at this point here, you can see all these lightning streak, white streaks on the image. So this is what happened when a CME hits us directly in the camera that is observing this. Okay, so it means that whenever you see this, so what happens is that the particles coming in, the cameras record it and it oversaturates it. So that's the reason why you can see all these white fuzziness streaks in it. Okay, and so this sunspot group that created this storm is 13 Earth radius. So it's the size of 13 Earths, and it consists of multiple M-class and X-class flare. Okay, and the X-class flare, as we talk about, they are anything above X20. So now this is a X25 to X45 flares, and you remember how we talk about how the classification saturates at X20. So this is the reason why, because we cannot categorize this storm anymore because it's too big. Right, the storm is too intense, and so this is and also this is what we call by a halo CME, where the CME is coming towards Earth. Okay, and like I said, the sudden brightness saturates the satellite image. Okay, and so these are some of the effects of the storm. Mainly, aurora being seen as low as Texas. Airline has to reroute because the flares actually disrupt HF and satellite communications. And there is actually more than 100 hours of communication blackout for the Antarctica research group. So nothing can be sent out, in and out. So we cannot even communicate with them. Now the astronauts on board ISS have to take cover from the high level of radiation. And a lot of satellites sustain degrees of electrical damage to their electrical systems. Okay, and of course a power outage due to the induced geomagnetic current. So this is another Carrington class storm in 2012 that kind of, I would say, got away because it was ejected out from the sun, but it never reaches us. Okay, so it's actually so it just so happened that Earth is at a good location where it's not in the path of this CME. Now you can see that the stereo. So these are the two satellites that observed it. Stereo B and stereo A. They are both looking at different different angles of the sun. And stereo A took the full brunt of the full force of the CME. And because you can see that there's a saturation in the image, but stereo B just look it from the side, right? And so this CME, this storm consists of not one but two consecutive CME storms. So it's a combination of both that make it such a intense storm. And unfortunately, fortunately I would say it didn't reach us. So, but we also cannot imagine that if it reaches us, the effects of this geomagnetic storm will be actually. We predict that it will be far greater than what we would have observed for the Carrington storm. Okay. So these are some other examples. Solar flare did actually delay rocket launch. Flights had to reroute. blackout in history. This is the famous Quebec blackout for the 1989 solar storm. We have in the US, there are damages done to nuclear plants. Okay, and of this is the funniest one. I think this is the cutest one. I think at least well, during homing. So during homing pigeon races, so what they do is that those you know that if you are familiar with homing pigeons, right? Homing pigeons follow the magnetic field line to reach back to a certain location. Now, when you have a storm coming in, that messes up the magnetic field, the Earth's magnetic field, and now the pigeons get confused and they don't come back to the original spot. So when you have a race like this, some of the pigeons can go missing, and the pigeon owners doesn't want that to happen, because then one homing pigeon takes so many years to train and thousands of dollars to to train them. So that would be like $1,000. If I'm a homing pigeon owner, I wouldn't want them to be lost. So they usually just call up, whenever they have a race, they will call up the Space Weather Prediction Center to ask if there's a solar storm coming at that time, when they're having the race, for example. So fun facts. Okay, so this is summary, okay, of all the effects, and okay, so one thing that I want to touch on is the radiation risk for astronauts. Okay, so even during without a solar storm, humans in space are already getting a certain dosage of radiation. Okay, but during a solar storm, the energetic particles can actually enter into the near Earth environment, and the astronauts can get a lethal dose of radiation just from a specific event itself, and they only have minutes to seek shelter. Okay, and even then, inside the ISS, they can still get a very little dose, and pretty much their career is done for their entire life, because they have already reached the dosage limit for their entire lifespan. Okay, so this is just a comparison. Okay. Of some of the Chernobyl radiation that the first responder are getting, and you can see here the range of radiation that one single solar flare can cause. Okay, and of course radiation can damage satellites, and so these are just some of the effects of that. It can degrade the material. It can actually damage the electronics within the satellites, and it's actually more so for small satellites like CubeSats, because CubeSats are smaller and they cannot protect themselves. They do not have the protection against a high level dose of radiation. And of course, the auroras, they are nice, but usually the airplanes will avoid going under a aurora zone. Okay, because all these particles can actually disturb the radio wave propagation, and it could lead to HF communication loss, and that's something that as a pilot, or as on the ground, they do not want that. They want to maintain a constant communication with the aircraft. So that's something that that they want to avoid during a storm, for example. There's also plasma irregularity in the atmosphere, and that could actually cause positioning errors in the GPS systems also. And of course also just now I touched on a little bit on the large geomagnetic storm induced currents that can actually blow out power lines, transformers on the ground, and that can actually cause a power outage for an extended period of time. Okay, and the other thing is it can also cause erosion in the gas and oil pipeline. Okay, so of course now we know all the effects of it, right? And so how are we going to mitigate it? Like, for example, how are we going to mitigate all these effects? Okay, disastrous effects of a geomagnetic storm. First thing is, of course, understand the science. Okay, without understanding the science, we do not know how to come up with solutions to avoid, to kind of like mitigate, predict, and all the effects of geomagnetic storms. So hence NASA actually has put in a lot of effort and have put in a lot of emphasis on the space weather research. So this is so pretty much space weather research covers everything, right? Covers a lot of things from the sun to the earth. So we have solar physics, solar wind physics, radiation belt physics, and storm physics, geomagnetic storm physics, and also the coupling between the magnetosphere and the ionosphere, the atmosphere or the ionosphere, deeper in the closer to the Earth. Okay, so these are all the current the fleet of heliophysics satellites out there that NASA has to actually observe and to study space weather. Okay, so it's really a huge fleet, and right now a lot of them are actually older, and so they need to be replaced. And NASA is constantly putting in new satellites, new flight missions to study the Sun-Earth connection and space weather. Okay, so the one thing is that one thing I do want to point out is that at NASA Goddard Space Flight Center, the Heliophysics Science Division, which I'm part of, they employ the largest group of research scientists, and we are really dedicated to studying and understanding space weather effects. Okay, and so we also collaborate with a lot of research scientists in universities through cooperative agreement. And that's something that I'm part of also as part of the cooperative agreement, that NASA use to engage in scientists in the US primarily. All right, and so they also led and developed ongoing and future flight missions and instrumentations for space weather research. So at Goddard Space Flight Center, we also have the Community Coordinated Modeling Center. And so this center contains the state-of-the-art, the best numerical model for space weather research and forecasting. Okay, and anybody can use it. It's a public website that you can go explore on your own. Okay, so this is the results. So this is something that a product of the CCMC, the modeling center, right? And so you can see here that you can see very clearly that there is a CME being ejected, and is actually observed by stereo A, right? And here you can see the yellow dot, which is Earth, is on the opposite end of the sun. So we are not observing this CME at all. And I think this is a 2012 event that I just talked about. Okay, so we also so at Michigan, people also develop a modeling framework to actually model the sun all the way out to Earth, and also and also predicting and try to model and predict what will be the effects of space weather on Earth itself. Okay, so a lot of this work is being done by done at University of Michigan. And of course, so NASA does space research, but NASA doesn't do operational type of missions. And so these are done by NOAA, which is the National Oceanic and Atmospheric Administration in the US. So they have this Space Weather Prediction Center, SWPC, that actually does the operational work of it. So what they do is that they will actually observe the sun using their satellites, and using those satellites, and then if they see anything, they will make certain predictions. If they see a sunspot, they will make a prediction. They will track the sunspot. They will make a predictions to whether that there will be a geomagnetic storm coming in. Okay, and then once they saw that, once they see, like, for example, a solar flare, that's where their job is to actually issue a warning. Just like a hurricane warning kind of thing. Being issued out, or an earthquake warning or something like that. So they will issue a warning to all their subscribers, telling them that, a storm is coming. So you guys got to do anything follow the protocol that any company will take. Like, for example, airlines, then they will try to divert all the planes around the polar region and things like that. Okay, so what they do, the forecasters at the facility in Boulder, Colorado, so they will look at the real-time data, and then they will predict based on the solar wind parameters, and then they will input into their model, and then they will issue alerts and warnings based on the model result to determine whether what classes of a geomagnetic storm it will be. Okay, so some of the challenges that we face right now. Now, space, like as I just described, space weather prediction lead time, okay, can be as low as a few hours. I mean, for a solar flare, the flare reaches Earth in under 8 minutes. So this is all we got, right? And then the CME can take from like hours to days. Of course, if you have days, that will be easy. They have days to actually predict it and issue out the warning. But if it's hours, the forecaster really only have 1 or 2 hours in order to input the parameters, run the model, and make a prediction and issue the warning. Okay, so this is how intense this forecasting job can be, right? And they have to analyze data in real time, and this takes years of experience, because you wouldn't want to issue a warning only to realize that, the storm is maybe a weaker storm that people wouldn't really care about. Or if you predict that it's a weaker storm and comes out to be a very intense storm, G5 type of storm, then of course your clients will not be happy about it, right? So it really takes years of experience. And quite frankly speaking, there's still a lot of unanswered questions in space weather research, and also the space plasma physics in the geospace environment. There's still so many things that we do not understand, okay? And so there's always a constant need for both operational satellites to monitor the conditions, and also new satellites, research satellites, to actually enhance our understanding or scientific understanding of this of space weather and the Sun-Earth connection. So beyond Earth, I'm going to touch a little bit on this. We have so space weather is no longer now between the Sun and the Earth. Okay, I mean, Moon is is within the Earth system, but we also talk about Moon space weather at Moon because right now with the Artemis mission, we are actually going into a lunar exploration era, but one important thing to note is that the Moon, because of its orbit, it only spends 1/3 of its orbit within the Earth magnetic shield, for example. So the shield actually protects against the solar wind, right? But 2/3 of the time it's not in the shield. So astronauts, or astronauts on the lunar surface, will be fully subjected to all this the lethal radiation for a CME or even the solar wind. The radiation from the sun. They will experience the full dosage of it. Okay, and so that's why space weather warning is very important for lunar astronauts. Okay. Now, the current mission that they have is the Lunar Gateway, which is going to orbit around the Moon, and it contains 2 instruments to actually study space weather at Moon. In fact, now in my group, we have some scientists, right? They are going down to Hawaii, right? Hawaii is the place where they have all these volcanic bands, and it simulates the volcanic bands on the surface of the Moon, and they are trying to determine whether some of these volcanic bands could be used as a shelter for astronauts during an extreme space weather event, for example. Okay. Now, space weather is also very crucial for robotics and flight missions to Mars. Okay, and also for future human exploration. Now, Mars lost its magnetic field a long time ago, so that means that Mars doesn't have the protection of a magnetic field against. It doesn't have that protection as Earth. So which means that the Martian astronauts, when they're there, they could be subjected to a lethal dosage of radiation just by being there. There's no even protection from it, right? And also even right now for some of these rovers, right? Whenever there's an issue for space weather, whenever there's a space weather warning, they have to predict whether the CME, for example, will reach Mars. If it does, then they have to do certain steps to actually either power down the rover to make sure that the storm experienced on Mars doesn't affect the electronics on the rover. Okay, and also not to mention that during the time, the 8 months travel, that's also where there is no protection against any storms, okay, by the astronauts. And a fun fact actually, so Earth is not the only planet that we can observe aurora. Okay, so aurora is seen as a light source because it's a light radiation, right? But we know that light radiation come in a whole spectrum, and at Mars we can also see auroras, but in a different spectrum, not with within the visible light range. And so we also have space weather at other planets, Mercury, and the giant magnetosphere. So as long as any planets with or without a magnetic field, we can study space weather. Okay, and just a quick another fun fact is that if you look at the figure right at the bottom here, you can see that, so this is Jupiter's aurora, and Io, what the closest moon to Io, the closest moon to Jupiter, also has a tiny footprint, aurora footprint on the Mars, on the Jupiter's aurora. Okay, so that's a fun fact. Okay, so last slide. Yes, so space weather is space science and space weather research really spans across many science disciplines, and you can see, so here we have from the sun's interior, interplanetary space, Earth geospace, and then we talk about a little bit about planetary space environment, solar system. We even talk about we even applies the principles of space weather into exoplanets and intergalactic systems. Okay, and so exoplanets, right? So and stellar astronomy, because for solar system we have the solar wind, right? But for other systems out there, they also have the stellar wind. That's what they call it, and how the stellar wind interact with the exoplanets. Okay, so that's something that that the astrophysics people are also studying. So there's still really so much that we do not understand, and right now we are just barely touching the tip of the iceberg. So I think that's my end of my talk. Thank you so much.
Thank you, Kang Kai. That was really great and I think super informative. We're going to jump into some quick fire questions just so we don't take up too much time, but we do have a lot of questions to go through. I will look at those in the chat first, just so I don't lose track of those. So we have a question from Jose. He says that from his understanding, radiation causes can mess with digital systems and electronic systems. So how do things like the rovers and Van Allen probes protect themselves from solar flares and storms when they are on missions, other than just turning off?
That's a very good question, actually. So pretty much turning off is the first thing that they do, right? And they will turn it off, and so once you power down, then the damage is, they minimize the damage to the micro electronics itself. Now there are certain so for example the Van Allen probe, as far as I know, right, they have protection against it. So they either thicken up the sides of the spacecraft itself, the sides of the spacecraft, to protect the electronics, right? Or what the spacecraft, some other spacecraft usually do when they go through the any radiation belt, was to if you see something bad, just go as fast as you can across. So what they do is that they do not stay within the radiation belt itself. So what they do is they do flybys. So they just cut every orbit. They will cut through the radiation belt for a short period of time, and then go out of the radiation belt and then comes in again. So they only observe. So throughout one orbit, they observe only one part of their orbit observe the radiation belt. Another example that does that was the Juno mission to Jupiter. Now Jupiter is a huge system. It has like at least 10 times, 100 times more intense radiation belt than Earth. And what the Juno spacecraft does is that it thickens up the protection, the lining of the spacecraft, and also it does all these flybys to minimize the time that it spends in the Jupiter's radiation belt. So these are some of the things that NASA does to kind of, the engineers at NASA does to kind of go around the problem of radiation for the satellites.
I know some of you asked what's the difference between CMEs and solar flares, but I think Jacob posted a very good kind of summarized answer in the chat. So if we have some time, we might look back to that questions, but I will just jump into the ones that we haven't answered yet. So Tianyu asked, do solar flares actually capable of causing huge damage to civilization, like completely knocking out internet connections and full blackouts? And I guess the kind of follow-up question to that would be, how big of a solar flare does it need to be for that kind of damage to be done to civilization?
That's a very good question actually. So solar flares are pretty much as we discussed a little bit and also from the video is actually mainly consists of X-rays, right? And X-rays are light radiation. So they are photons, okay? And so these radiations are not affected by magnetic field. They don't follow the magnetic field. So they only traverse in a straight line, right? And so that means that the Earth's magnetic shield doesn't protect against solar flares. But the only thing that provides protection against solar flares is actually Earth's atmosphere. Okay, so it can actually it does not cause it usually cause changes in the ionosphere and disruption in the HF communication, and also a solar flare can increase radiation outside of the can increase radiation for astronauts outside of Earth's atmosphere, right? But solar flares cannot affect anything below the atmosphere. So like for example, power blackout and all these things. That's not what solar flare does, but that's what the CME does, because the CME can affect the magnetic field around Earth, and which is actually connected down all the way down to the Earth's surface. So that's the effect that we are feeling. So I would say that solar flare can also cause a lot of damage to electronics, to technologies that we have. But I would say that damage is still there. It's hard to define whether it's large or small and things like that. But even a small flare can actually cause significant damage already. So it doesn't have to be like end of the world type of flare. But it doesn't wipe out human civilization,
Yeah.
right? Right. So I always say that if I'm not on my internet, this is the end of the world for me. Kind of. But no, unfortunately, it's not. So.
Hopefully we never have to experience that kind of level of solar flares.
Yeah, I know. Hopefully.
So a follow-up question from Tianyu actually is, so we do know that space weather affects Earth, but can human activities which cause global warming on Earth also in turn affect space weather? Is there or things that we can our actions on Earth actually cause an increase in kind of flares and things like that?
That's a good question actually. So I would say that there hasn't really been a lot of research on that to suggest that there is a two-way effect. But human activity definitely can actually affect how space weather affect Earth. Human society because for example, human activity, like how we design certain stuff, like how we design the electrical grid system, right? How we design certain technology, how resistance are there are these technologies to how resistant are they to effects of space weather. So something that I think what human activity does can affect how much we are affected by these storms.
Right. Okay. Let's see. Okay, this is quite a good one. So when small parts of CMEs reach Earth, it reacts to form auroras and reacts with other particles. But do they only happen at the poles, or why is it that they more commonly happen at the poles?
That's a very good question. So it requires a little bit of understanding of how the Earth's magnetic field works. Okay, so the reason why it affects the pole is because the polar region contains magnetic field lines that is actually directly connected to the sun or into the to the interplanetary space. Okay, so these are what we call by the open field lines. They are open because they are connected directly to the interplanetary space, right? The interplanetary medium. Now the lower latitudes ones near the equator, or even like at mid latitudes, they are actually closed field lines, because those field lines actually are on both ends of the field line are connected to Earth. So the particles from the sun or from the solar wind cannot leak into those closed field lines, but they can only leak into the open field lines. So, and we know that auroras are caused by all these solar wind particles coming in, entering the atmosphere and interact with our atmosphere to create all these beautiful lights, right? So that's the reason why that's really the qualitative way of explaining, why auroras only occur during normal times. It only occurs at the higher latitude around the polar region.
Okay. So from Carl, he asks, is there a boundary latitude that auroras cannot go beyond? So kind of following up on that poll questions, is there a boundary that we don't, after a certain point, that tend to get less effects? Yeah.
Technically, I would say theoretically there's none, depending on what kind of condition we're talking about, right? When we're talking about quiet times without the storm, nice weather, nice space weather, so to speak, they only occur around the high latitude polar region. And as I shown from the let me go back to that. Let me go back to that picture here. This very cute picture. Let's see, where is it? Yes, here. So right here, and you can see that the cool and exciting and normal is all at the high latitude, but the moment we are at near the equator, that's where we start to get worried, because that's where a storm can do the most damage to us actually. So that, to answer the question, there is none actually. Theoretically, the auroras can go all the way down to the equator, depending on how intense the geomagnetic storm is.
But if it does, then we should be quite concerned.
Yeah, we should be quite concerned, yes. Yeah, you're right. Yeah, we should be quite concerned.
We should be a little concerned if it does actually reach.
Yeah, depends. I mean, depends on those satellite operators will be sweating, and they'll be like, oh, we lost like $1 billion satellites and things like that. But for us as space physicists, I mean, we will be sweating over the loss of internet and things like that. But we'll be like, yeah, you can answer a lot of the science. We now we know, So it's really a balance between, I guess, how much damage you can do, and then but as a physicist, we always want to have that data point of it being the strongest, that we experience the strongest storm. Then we can know that what the strongest storm what effect can it have on us, and with the knowledge, then we can predict other storms in the future, other intense storms in the future, or super storms in the future. So but it's really a question of, do we really want that? We want that to happen, but yeah.
So we do have a couple of questions about the effects of radiation on our astronauts in space, specifically as well as the ISS. So Nyat No, I hope I'm pronouncing your name correctly. How much cosmic radiation does the ISS regularly receive? And is this a significant enough amount to have detrimental effects on the cells in the human body for astronauts? If so, how do the astronauts protect themselves from these radiation?
That's a very good question, actually. So I do not have the number, I do not have the exact number, but as far as I understand, astronauts do so. Besides all the other radiations that they encounter when they are in space, galactic cosmic ray is another one that is actually a problem for them, but the dosage is actually very small. And as compared to the dosage that they receive from, say, being in the Van Allen radiation belt, so or even like a space weather event, so it's very small. But one thing that is very interesting, and like how I mentioned, and that I mentioned earlier on, is that the solar wind actually propagates all the way to the edge of the solar system, right? And it only stops in the boundary where it interacts with the when we interact with the interstellar medium. Now, the galactic cosmic ray comes from the interstellar medium. Okay, so anything outside of the solar system. Now, I believe that we do. There are research that suggests that during solar maximum, means that the sun is super active and the sun is constantly spewing out the solar wind out into the rest of the solar system, we do see a decrease in galactic cosmic ray. So we kind of make that relation that maybe the solar wind is the one that is protecting us against some of these cosmic ray out there. But again, we only have 2 spacecraft, Voyager 1 and 2, that that barely touches the edge of the solar system. So we really do not know much about it either. So a lot of these are just theoretical work that's being done right now.
So Pranav has a question. So besides instruments like the magnetometers that you mentioned, what other instruments can we use to study magnetic field disturbances, CMEs, and solar flares, or if there are any others?
That's a very good question. So magnetic field measurements, of course, is the most fundamental one. Okay. For most NASA missions, they also have what we call plasma instruments. So the plasma instruments actually measures the particles itself. So the particles coming in, right? The electrons and ions coming in, and those instruments collect them and try to derive like a density, a velocity, parameters associated with it. So those are the plasma instruments. And ions instruments are different from protons instruments, and they are very different from electron instruments. So these are three separate instruments, and usually they come in one suite of instruments, okay, in one suite itself on the spacecraft. We also have X-ray instruments, neutron spectrometers. We have spectrometers on board to study them. Sometimes we have cameras. So some of the videos that we see for the CMEs and to look at the sun. So some of the space weather satellites that we images that we see to look at the sun, they also have cameras on board that look directly at the sun, and some of these cameras are not the usual DSLR camera that we take photo with, or even your phone cameras. They work the same, but they have to be built to be able to withstand the intense radiation. For example, let's say a CME hits, and they have to make sure that when the CME hits, the camera it's not disabled. So it's able to stay operational throughout the entire mission phase. So for example, cameras are there. There are also other instruments that many other instruments to study that. So just some of the ones that I can think of right now.
Just to kind of add on to Kang Kai's answer for you guys, is that if you're looking directly at measuring solar flares and radiation and all these things, so there are a specific set of instruments that you can use. But then if you can look at, if you are able to get creative and look at other ways of studying space weather, so maybe like looking at the effects of Earth, so you can use data tracking blackouts on Earth to see if there's any effects of space weather like that. That can work as well. So try to think out of the box, and actually later on in this, I think sometime in October, we're actually planning a webinar for how to use satellite images of Earth to kind of track space weather effects in a sense. So that's some of the things that you can start thinking about now as you are planning your project proposals. But yeah. We have a lot of questions. I don't know how much time we have. It might run. So I see a lot of questions about the Van Allen belts and radiation belts specifically. But I think we might shelve that for actually your seminar next week, because Kang Kai is coming back next week, same time, to kind of talk a bit more about radiation belts and the Van Allen belts. And actually later on, we also have someone else coming in to talk about the Van Allen belt specifically. So we might be able to shelve those questions for then. But I think a fun one from the audience is, what is it like working at NASA? And what's your day-to-day life? And what's your favorite part of working at NASA?
So to answer that question, I'm not sure. So back when I was a student, back when I was younger, on Facebook, right? And we always have this. I don't know whether Gillian, I don't know whether you remember this, but they have what people think I do, what I think I do, right? The memes, right? What I think I do and what I actually do. So I'm just going to give you the what I actually do, not to sugarcoat anything. So well, actually, quite frankly speaking, it's actually quite exciting to be working at NASA. Because I'm a foreign national, a lot of things at NASA is definitely off limits to foreign national. You have to be a US citizen to do that. But even then, the research that we do at NASA is actually very exciting. Of course, at NASA they do a lot more engineering stuff. Building instruments, planning for like flight missions and things like that. But just from the research, it's actually very exciting. There's a lot of people working there. They are experts in their field, and we usually collaborate on research projects. And people are there, analyzing data, and so for me it has been quite a fun experience, studying some of the science, that I really love. So yeah, and also it's a very good environment. People are very nice to each other. It's not a stressful environment. It's very laid back, and we can just have coffee, and then people just start talking about science, about things that they love about, or things that they're working on. And I think the environment is pretty much also shaped by the people working in there, because people working in there, as far as I know, they really enjoy what they do. It's not a job. It's not a 9 to 5 job for them. It's really a career, and really something that they have dreamt of working since they are young, or so they're really passionate about their work, and really that creates a very highly positive environment at NASA, especially at Goddard Space Flight Center that I'm based in.
So guys, it's a possible dream to aspire to work at NASA. Yeah, I think just to kind of sum up everything, because we probably won't be able to go through all the questions, unfortunately. I'm sorry, guys. we'll try. So I think our student facilitators are actually in the chat. So we have active Discord channel, which Gankai is also there. Gankai also joined the Discord channel. So if you guys have questions that you really want to ask, our questions and inquiries on the Discord channel is always open. We're always happy to answer any questions you have there. But yeah, just to kind of like wrap things up, what are good sources for books or information on space weather that maybe the students can access so they can do more research into it in their own time?
Yeah. Quite frankly speaking, you right now with internet, you can find a lot of information on there. Yeah, and quite frankly speaking, the slides that makes up today's presentation, most of them can be found in the on the internet. So you can go to nasa.gov. They have a very good explanation of what space weather is. If you look under heliophysics or or planetary science, they have a lot of information on there. NOAA, NOAA Space Weather Prediction Center also have a lot of information on there that you can look up. So these are the two most important, I think, source of information. Books wise, I wouldn't recommend a lot of the books, because some of the textbooks are really mathematical based. So if you want a qualitative type of description of space weather, those might be, for the younger students, those might be a little bit advanced. But there are some books that I think, let me see if I can find some on the bookshelf, that provides a more qualitative description rather than mathematical.
I mean, we could always just kind of email the students in the resources. Once if you have a couple of suggestions, we can always send them an email after with all the suggestions. But yeah, guys, like I said, Gankai is coming back next week to do another webinar. So actually, I'm going to link the registration link to that webinar right now in the chat, so that you guys can just sign up. We'll also send out an email sometime over the weekend for you guys to register.
Jillian, will you also be sharing these slides with them?
I'll share the video recording, but if you want, you can send the slides over to me. I can also send it out into the email that they can refer to it in more details.
In fact, actually, because I have linked, I have like web page of all the references of the or the pictures that I've used, and so those are actually also good resources for them to go in and take a look. So
yeah, that's true. That is true. Yeah. So guys, we'll send out the slides along with the recording. to you guys, so then you can refer back and then also look through it in a bit more detail about what was covered today. But yeah, so I don't want to take up any more time, everyone's more time. I think this has been a really great first session, first knowledge sharing session. Is a great way to set the foundation for the rest of the webinars that we have coming up. And yeah, I think if everyone can give Gang Kai a big thank you for his sharing today.
Thank you for inviting me.
Next week.
Thank you for inviting me, and thank you for spending the evening with me. So
no, it was super fun. It was super fun session, and I think the thing about the pigeons really had a lot of us quite amused. We're like a lot of the holding pigeons not getting lost.
I know that's the funny thing. You know, I mean, you would never know that, you know, even for pigeon racing, they will care about space weather. So
yeah,
they know about that. They know about it. Yeah. So very funny. But anyway, yeah. Thank you so much, guys. Thank you so much.
Thank you, everybody, for spending your evening, morning with us, afternoon. We look forward to seeing you next week. So keep a lookout for the email with the webinar links as well. We'll actually be sharing a couple of webinar links together. So yeah, thank you all.
Thank you. Bye-bye.
Bye.